So last time I told you all about Mumford's geometric invariant theory for reductive groups, and the plan for tomorrow and Friday is to talk about the recent work in geometric invariant theory for non-reductive groups, so sort of general linear algebraic groups. And today is a kind of bridge between the two, a sort of interlude where I'm going to talk about some applications of reductive GIT and the structure that instability has in reductive GIT. So the parts of today's lecture will be maybe a little bit more technical than yesterday and the day before, but I'm gonna try to make the general idea as clear as possible, even if the technical details are tricky to understand in real time. So let's get started. Right, so last time we saw that given a reductive linear algebraic group, G acting on X, a projective scheme or variety, we saw that there exists an open so-called semi-stable locus, which has mapped to this thing, the GIT quotient, which was projective invariant. And this thing is a good projective quotient. And the other thing that we saw was that crucially, XSS, the semi-stable locus, is determined or can be computed by a Hilbert-Mumford criterion. I guess I should say the Hilbert-Mumford criterion because it was the original. So this means, as I was saying last time, this thing really means that we can actually compute what this semi-stable locus is without having to know invariance. And that's enormously useful because computing invariance is hard. Okay, so let me start today by just talking about some applications of this. So I'm not going to get into any of the details here. I'm just going to kind of rattle off some stuff that you may have heard of or may not have heard of, sort of applications of reductive GIT to famous moduli problems. So the first one is about curves. Okay, so if we take G greater than or equal to 2 and consider the problem of classifying, let's say smooth, maybe projective algebraic curves. So of genus G. So a way you can do this with GIT is if you take your curve C, then if you take a sufficiently high power of the canonical, you can embed it into a projective space. And this thing corresponds to a point in a certain locus, which I'll call K, inside what's called a Chow variety, PR1D. So this thing here parameterizes algebraic cycles in the projective space of dimension 1 and degree D. So you could do this with a Hilbert scheme, which is a thing that parameterizes closed subschemes, but I'm going to do it with the Chow variety because it relates to something I want to say later. So for this, you want n, which is this number here, to be sufficiently big. It actually doesn't have to be that big, but it needs to be big enough. Okay, so if you do this, so this parameterizes the smooth projective algebraic curves of genus G. And you get an action of SL, I guess it would be R plus 1 on the closure of this locus K. And this you can apply reductive GIT to, and this gives you the famous moduli space of stable curves. So I'll just remind you, in case you have forgotten or haven't seen before, what a stable curve means. It means all singularities are nodes and the automorphism group is finite. So this here means you're allowed to have. So we've taken smooth curves and we've compactified it. This thing is projective because it's a projective GIT quotient. We've compactified it by allowing our curves to develop singularities, but we're only allowing it to develop nodal singularities, so sort of things that analytically look like this. So you're not, in particular, you're not allowed to have things like y squared equals x cubed, cusps. Like this is bad. You're not allowed that. And sort of remarkable thing is that if you impose these conditions, you actually get a nice compact moduli space. It's a projective variety. So that's maybe one of the most famous applications of what I called the main theorem of projective reductive GIT last time. So that's a sort of famous moduli space you can get with this stuff. And the actual analysis of a semi-stability is still complicated. It's still a substantial theorem that you actually get mg bar, but you can use the machinery from last time. Okay, and then the next one is an application to coherent sheaves on coherent sheaves F on a projective scheme. Projective scheme. Maybe I'll call it Y. And then, so this one, the way this works is if I take M sufficiently large, bigger than N sufficiently large, then I can consider points in a so-called quat scheme, which parameterizes quotients that look like this. I can realize F as this coherent sheaf I'm interested in as a quotient of this thing. And this lives in some locus I'm going to call Q, which in turn is inside a quat scheme. And this thing parameterizes, it parameterizes all quotient sheaves of OY minus N with the correct Hilbert polynomial. So let me write that down. So this parameterizes all sheaves on Y. This parameterizes, let me say it like this, quotient sheaves of OY minus N to the power Pn with Hilbert polynomial Pn. So if all of this is just nonsense and you don't know what it means, then I wouldn't worry about it too much. But I'm just saying you can come up with some parameterizing these reasonable coherent sheaves, and you get an action of GLPn. So you can think of this thing as OY minus N tensor a vector space of dimension Pn. So you can act on that vector space by GLPn. This gives you an action on this locus Q. Well, take the projective closure of it. And this has projective GIT quotient, I guess MP, which is the moduli space of stable coherent sheaves on Y. Okay, so what does semi-stable mean? Semi-stable means that for all subsheaves like this, we have little p of f prime is less than or equal to little p of f, where little p is the reduced Hilbert polynomial. So that's where you take the Hilbert polynomial and you sort of normalize by the leading coefficient. So if you haven't seen this before, you can think of a special case, which is vector bundles on Y equals C smooth projective curve. And then in that situation, this condition here reduces to this condition on slopes. So you define the slope to be the degree over the rank, and then you require this the inequality to hold between the slopes for all subbundles. So this is probably familiar from the talk of Bridgeland stability conditions and so on. Okay, so that's just a quick canter through two of maybe the most famous applications of the reductive theory. Before we move on to what I really want to talk about this time, which is what about unstable things? So what we saw last time was that, you know, in this situation here, you get this open, nice semi-stable locus, and it has a good quotient, and it's projective, and that's all very well. But in the process, you've kind of thrown away everything that's in the complement of this semi-stable locus. So imagine that this was some moduli problem. You're trying to classify some particular objects, and you wrote down X, which was some space that parameterizes those objects with some notion of equivalence captured by a group action. Then GIT says, okay, I'm not going to classify all the objects for you. I'm just going to do most of them. So a reasonable question to ask, having seen this, is what can we do about the stuff that's unstable, the stuff that gets thrown away by this sort of traditional moduli problem? Okay, so the kind of related question that you have to answer first is, can instability be measured? Is there some reasonable notion of how unstable something is?
Can you lift it up a little bit?
Sorry?
Can you go up a little bit?
Oh, yeah, sure. Sorry. Is that okay?
Yes, sir.
Okay. I'll just leave that up for a second while I talk about what's going to happen next. So what I'm going to talk about next is something called the HKKN stratification, or maybe the instability stratification, which crops up in reductive GIT, and which is a way of measuring instability. And I want to talk about this really for two reasons. One is that it's an important part of reductive GIT. It's an important piece of structure that has interesting generalizations. And the other reason to talk about it is that it's a place where you will see non-reductive groups cropping up sort of in nature, even if you start with a reductive problem. So let's get onto that. Okay. So if we just recall what the Hilbert-Mumford criterion tells us what semi-stability is. So a point is semi-stable if and only if we have this Hilbert-Mumford function being positive for all parameter subgroups, all homomorphisms from GM to G. And this was also the same as 0 being in the convex hull of the T weights of GX for all G in G. Okay, so I'm asking, can instability be measured? And I'm telling you that one way to say whether something is semi-stable or not is to say, well, is the origin in this convex hull? So a very reasonable way to try to measure instability would be to say, okay, if you're unstable, that means you're not semi-stable. So it means the origin is not inside this convex polytope. So you could just ask, well, how far away is the origin from being on this convex polytope? What is the closest point on this convex polytope to the origin? And that is essentially the idea of this whole picture. So in order to talk about how close is the origin to this convex polytope, I'm obviously going to need a way to measure distance on the space where these polytopes actually live. So recall this thing lives inside the dual of the Lie algebra of T. So it's living inside some vector space. So I'm going to need something like a way of measuring distance on that vector space. So the way that you do that is you choose this thing, which is a positive, definite, and Weil invariant integral valued bilinear form on this set, which I'll write like this, and this is just the set of these homomorphisms into T. So, okay, so it's essentially an inner product on this Lie algebra. But I require something, I require it to be Weil invariant because what I really want to do is to have a way of measuring the size of a given co-character, a given one parameter subgroup. And so the way I'm going to do that is I'm going to take this and I'm going to conjugate it so that it lies in T, and then I'm going to apply this bilinear form to it. But in order for that to be well defined, I need the whole thing to be invariant under the Weil group. So that's the reason for this condition here. It's really just a way of measuring distance in here in a way which is invariant under conjugation. So a lot of the difficulty of understanding the HKKN stratification comes from the fact that you have to think about conjugacy classes and you have to think about Weil invariants and so on. So if you're confused, I would encourage you to just think about the case where G is a torus, because in that case, it's a whole lot simpler and lots of things get easier, and you don't have to worry about things like conjugacy classes quite so much. Okay. Right, so yes, what the reason for the Weil invariance. This tells you that this thing is a well-defined norm on this space. Right, so e.g., let me give you a nice example. If G is SL n plus 1, then take the killing form. So this is sort of the natural inner product on the Lie algebra. And in fact, if G is SL, then this is really the only choice you have up to scaling. So there's no choice at all. In general, there may actually be a choice, but for SL, there's no choice.
Are you making a choice on what torus you choose?
I'm sorry?
So T is a torus, yeah?
Yes, there is a choice of torus in the background. Sorry, yeah. So for the whole of today, I'm fixing a maximal torus T of G, and that's a choice. But things don't depend on that choice in any meaningful sense, because we're going to be sort of sweeping out by the action of G and thinking about conjugacy classes and so on. So we'll get an equivalent picture if we choose a different maximal torus. Okay. So just returning to this characterization here, another thing you could have said when I said, well, how do you measure instability, is to say that given that Hilbert-Mumford criterion tells me that semi-stability is equivalent to this condition being satisfied for all one-parameter subgroups, you could say, well, I want to look for the one-parameter subgroup that maximally violates this condition. So the lambda that gives you the most negative answer. And if you think about it for a little while and maybe try some examples, you'll see that that's not quite right, because you can replace lambda by lambda to the n, and that multiplies the weight by n. So it's not going to be bounded. So what you actually need to do is normalize it. But if you suitably normalize it, then this idea will in fact work. So, and that's another use for this. So let me just define the normalized Hilbert-Mumford function. And this is, I'll call it capital M, and it's just the usual thing, but divided by the norm of lambda. So this is going to be the right thing to try to maximally violate the inequality. Okay, so let me write capital lambda x to be the set of lambda such that you achieve the infimum of this function. So a priori, this thing might not be bounded. In fact, it is. So there's this theorem of Kempf. So one of the k's in HKKN is for Kempf. And it says the following. So for fixed unstable point x, then first of all, there exists a lambda which achieves achieving this infimum, i.e. this capital lambda x is non-empty. So you should think of this set as being like the worst one-parameter subgroups for the point x. So sometimes these are called one-parameter subgroups adapted to the point X. But really, they're the ones that maximally violate the Hilbert-Mumford criterion, that are sort of the witnesses to how unstable that point is. Okay, so that's the first part of the result. The second part is, well, okay, so I've said it exists. So you might want to know, well, is it unique? And the answer is sort of. So there exists this parabolic subgroup, depending on X, which lives inside G, such that P of X is equal to P lambda for any lambda, which is a worst one-parameter subgroup for X. So this notation here means well, yeah, let me write down what it is in a second. And then the third thing says that, so this third condition is really the uniqueness statement. So any lambda 1, lambda 2 in here are conjugate by Px. So what this is saying is that up to conjugation by this parabolic, which depends only on the point X, the worst one-parameter subgroup is essentially unique. That's the point. So let me just tell you how you get this P lambda then. So this is the set of G and G such that the following limit exists. So G, of course, is affine, so this limit might not exist all the time, but for some elements it will exist, and this is this. But let me just show you that this definition is consistent with a similar definition I gave for parabolic groups before. So let's just say, actually, let me write this down here. Okay, so if G is SLM plus 1, then P lambda is the parabolic that we've already seen, preserving the weight filtration of lambda. So if you write down the weight filtration as a, so this is like SL of some vector space V, and you write down the weight decomposition of lambda, that gives you a filtration. And you can define the parabolic, which fixes that filtration in the same way that I did in the other lecture. So this thing will look like T to the alpha naught times some identity matrix, T to the alpha 1 times some identity matrix, etc. Choose coordinates so it looks like this. So these are block diagonal with T to the AI, T to the alpha I on the diagonal, with alpha naught basically to alpha n, and then P lambda will look like the thing that I drew before. So it's like the thing where you require it to be block upper triangular, like that. So this is a really good example to fix in your mind when I talk about the next stuff, because it can be quite abstract, but for SL, it's sort of concrete. You can sort of write down what it is. Okay, great. So that's what this theorem says. It says that there is a worst one-parameter subgroup, and it is unique in the following sense, up to conjugation by a particular parabolic. Okay, so that gives us a kind of way in to measure instability. So the idea is to associate to X in X a worst one-parameter subgroup lambda in capital lambda of X. So we're going to sort of index points of X by their worst one-parameter subgroups. That's the basic idea. Okay, so let me first talk about the case where G is a torus, because that's easier to understand. So given X in X, I can just associate to it this point, which I'll call beta of X, which lives in the dual of the Lie algebra of T, and this is the closest point to 0 on this convex thing, where I'm using this norm that I talked about before. So the picture is very straightforward. You just draw the Lie algebra, and then you maybe have some weights, and we're saying that suppose X is unstable, so that means that the convex hull of the weights won't contain the origin. So you draw the convex hull like this. Maybe it looks like that. And then you try to find what's the closest point to the origin. So that would be something like this. So this point here would be beta of X. And hopefully you agree this is a reasonable way to measure how unstable the point is, because it's measuring the failure of the Hilbert-Mumford criterion to be satisfied. Okay. Sort of conversely, given a point in this Lie algebra, you can define lambda, a one-parameter subgroup, via the inner product. So the one way to think about this is giving you an identification between the dual of the Lie algebra and the Lie algebra itself. So it's giving you an identification between characters and co-characters. And if you have once you pass to the Lie algebra of T, so you pass from here to the Lie algebra of T using this identification with its dual, and then you can exponentiate the results to get a one-parameter subgroup like this. Okay, and now I'll just give you some notation here. I'm going to define P beta to be P of lambda beta. So it's the one-parameter subgroup that corresponds to lambda beta under this description that I gave here. And again, you can just think of G as being SL this whole way through, and you won't lose much. Okay, so having got that, I can then define Y beta SS. So this is the points of X such that this beta of X is the point beta. So it's the set of points such that when you draw the T-weight polytope and you take the convex hull of those points, you end up with a polytope whose closest point is the point beta in question. Another piece of notation I need is what they call Z beta SS, which is a set of points in the lambda beta fixed point locus, such that this is true. And I have a map from here to here, which is called P beta, and this takes the point X to its limit under lambda beta. Okay, so let me draw you another picture. Let's say beta is here, then I could take maybe something like this. So this would be Y beta SS, and then let's use a different color. Why not purple? Then this here is the things that will be in Z beta SS, and P beta is sort of the map which kind of projects the weight polytope onto the Z beta SS part. All right. So you can think of this, if you want to, as being, this is sort of like taking the associated gradient of a filtration. That remark may be a little bit cryptic, but to some people it will perhaps make sense. Okay, so now I've got all the notation. Sorry about that. It's a little bit heavy, but there's no way around it really. And now I can tell you the theorem.
Can I ask a question?
Sure, yeah.
I just want to clarify your two pictures. The top picture
Yep.
is happening in the dual of the Lie algebra, and the bottom picture is happening in X? Or am I confused?
No, sorry. All the pictures, both pictures are in the dual of the Lie algebra. So sorry, it was a little unclear. When I draw this picture, what I'm saying is, if I had a point that had this convex thing as its weight polytope in the dual of the Lie algebra, that would be in Y beta SS. And if I had something that was whose weights gave me the purple one with my convex hull, then that would be in Z beta SS. So it's not literally true that this is Y beta SS. I'm saying this is what the weights of something that is in Y beta SS would look like.
Right. Okay.
Thanks for that. Sorry, that was probably unclear. Okay.
Can I also ask,
yes.
point beta of X, does it have rational coordinates?
Yes. So there is something I'm maybe slightly sweeping under the rug, which is that it makes life a little bit easier if you work with rational one-parameter subgroups rather than actual one-parameter subgroups. So you can, where's it gone? You can sort of tensor this with Q, if you like, and that makes things easier. The point being that it's not going to make any difference. You really only care about this thing up to scaling. So you should think of these as being rational coordinate points. Okay, right. So now I can tell you the theorem. So this theorem is saying that there is a way of measuring instability, and it kind of divides up points of X according to how unstable they are. So this is the Hesselink, Kempf, Kerwin, Ness stratification. Okay, so G is reductive as always, and with a choice of this inner product here, which again, if it's G is SL, I can just take the killing form, and let's suppose that this thing is acting on a projective variety linearly. Okay, and then the theorem says, then there exists a G invariant locally closed stratification, which is called the HKKN stratification for obvious reasons, and it looks like this. So X is a disjoint union of these betas in some index set S beta. So where so it's indexed over a finite set curly B, which I guess is going to live inside here. So it's indexed by a finite set of points in here, and it has the following properties. So the first one is that the open stratum is the semi-stable locus. So that makes sense, because if you're semi-stable, that means your the origin is contained in the convex hull of your weight polytope on every point of your orbit, every point of your G orbit. So a semi-stable point should live in the kind of zero stratum, which corresponds to zero, the origin in here. Okay. So that's the first thing. So this says it sort of generalizes the semi-stable locus, if you want. The second thing is that S beta can be written as the G sweep of this Y beta SS. So you can sort of choose a maximal torus, do the whole thing for this maximal torus according to this definition, and then sweep it by G, and that's how you can get S beta. And this thing is equivariantly isomorphic to the following, which is by definition, I take this product and I quotient by P beta, and the action is given by H on Gx equals GH inverse HX. So this part is maybe technical, and it's not exactly it's not super important. I'll tell you in a second what it means really, what the upshot of it is. And the third thing is just that there's a reasonable sense in which this is a stratification. So if I take the closure of a stratum, then what I get is those strata that are sort of bigger. So the closure of a stratum contains more unstable points, if you like, points whose closest point to the origin is further away than the one I started with. Okay, and then the point of two, at least from my perspective, what I want to say is it says that quotienting S beta by G is the same thing as quotienting Y beta SS by P beta. Right. So if you imagine we want to, imagine we've got, this is coming from a moduli problem. We've got some things we want to classify, and we can do the classical reductive GIT to get this moduli of semi-stables, but then we'd say, okay, well, what about everything else in this stratification? And the obvious thing to try to do is to just get quotients of all the other strata. But the whole point is that these strata are unstable. So we will not get nice quotients if we just try to quotient them by G. The semi-stable locus in here is going to be empty, because the semi-stable locus is exactly this, and we've already dealt with that. So what this tells you is that you can do this sort of sleight of hand, where instead of quotienting this by this, you can quotient this by p beta. And that's an equivalent question. But the sort of technical reason why this is better is that p beta has more characters in general. So there's a sort of wider range of linearizations in some sense that you can use over here. You have a little bit more freedom here than you do here. However, the problem with this is that p beta is not reductive. So I told you what the unipotent radical of p beta was. Like if G is SL, then p beta is some block of a triangular thing, and the unipotent radical is exactly the stuff where you've got identity matrices on the diagonal blocks. So it's not trivial in general. So you can't use Mumford's reductive GIT. So one of the motivations for non-reductive GIT is to kind of enhance our ability to solve moduli problems by quotienting these unstable strata. This sometimes gets called moduli of unstable objects. So that's one of the motivations for non-reductive GIT, which is something that I'm going to talk about tomorrow and the next day. So that's really the upshot of this theorem, I would say, that if you can quotient these unstable strata, then you have a way of classifying all objects in your moduli problem, not just the so-called semi-stable ones. So it's a kind of perspective shift on what it means to solve a moduli problem, I would say. Okay.
Can I ask, was the third term in the second statement, I guess, the G times P beta YSS beta? Yeah, what is that?
Yeah, so this, by definition, that's just this. I'm just defining this to be this. This is just notation for the thing on the right.
Yeah, but the right-hand side is, so far, it's not defined, right? Because you just said it, you need non-reductive GIT.
Okay, so this is a quotient you can actually do, even though p beta is non-reductive, because essentially the action is free, and so it turns out you can actually do this. So this quotient is not the quotient that you need non-reductive GIT to do. This quotient is just a way of saying what this looks like, and that's sort of perfectly fine, and you can do it. The quotient that is the quotient that is difficult is the quotient of y beta SS on its own by p beta. That's the point. So you could, if you want, have written. There's a statement. There's a version of this statement which is in terms of quotient stacks, if you like, that sort of thing, which says that the sort of quotient stack of this by G is equivalent to the thing of y beta SS by p beta. But I really like this just because this is the original way it was written. Okay. So there are two other things that I should mention before I get on to talking a bit more about this. Just things I would be remiss not to have brought up at some point. So one of them is the connection to symplectic symmetry. So let me briefly talk about that. So in fact, I'll start a new page. Why not? Okay, so symplectic quotients. I'm not going to get into this in any amount of detail, but I will at least say it. Okay, so if K is a compact Lie group acting on X, a symplectic manifold, i.e. It's a manifold with a closed, non-degenerate two-form, omega, and let mu, so this mu is a different mu from the Hilbert-Mumford mu, sorry. So this thing, so this is the dual of the Lie algebra of K. So let this be a moment map. Then there's a symplectic. There's a symplectic quotient. You take the pre-image of the origin and you quotient it by K. Okay, so what's the relationship between this and GIT? The point is that if I take a, say, smooth projective variety over the complex numbers, then it's scalar. in particular, it's symplectic. If so, and if it has an action of G, the complexification of K acts on X linearly, then no, sorry, let me say that differently. Sorry. So if a reductive G acts on X linearly, then there exists a maximal compact K in G, preserving the symplectic form, which is the Fabini-Studi thing. And a moment map such that, and then this is the punchline, this is called the Kempf-Ness theorem. And it says that a symplectic quotient is homeomorphic to the reductive GIT quotient that we've seen. So it says that the symplectic quotients are, at least up to homeomorphism, the same as the GIT quotient of the by the complexification. And there's a kind of enhancement of this involving unstable strata. So given a choice of this invariant inner product, we can consider the Morse stratification associated to the norm square of the moment map, which is, let's move this down here, from X to R. And then the theorem is, which is due to Kerwin, that this stratification coincides with the HKKN stratification. So if you've not seen Morse stratifications before, then the picture that everybody always draws is you're supposed to imagine a donut on its side, and the Morse function is the height. And the Morse stratification is you start at some point on here and you just flow down. Imagine pouring water on this donut, and almost all the time you'd end up down here, but maybe some of the time you'd end up down here. So you get a stratification of this thing into locally closed pieces, depending on where you end up when you flow down under gravity. And that is essentially the idea of this Morse stratification. And the theorem says that this HKKN stratification, which is a purely algebraic thing, you can define it symplectically. Okay, and then one other thing that I need to mention in passing, which goes under the heading of beyond GIT. So this is for people who like stacks. So Halpern and Leisner has generalized the HKKN stratification to stacks X by considering maps from a stack that he calls theta, which is just, I take A1 quotient by G, that I'll use brackets, that quotient stack there. So this is a huge generalization of this this story that you see in reductive GIT. And what this is saying is that the fact that you see this when you set up your moduli problem using GIT is not some kind of accident or artifact of GIT itself. It's in some sense part of the structure of stability in moduli theory itself. So it's something fairly deep behind all of this, I would say. Okay, so let me say no more about that. So finally, I just want to give some examples of these stratifications, because I think it's quite hard to take it all in without having seen any examples. So let's talk about a couple of those. Right. So the first example is maybe the nicest, moduli of n points on P1 up to, let's say, SL2. Okay, so recall, I said last time at the end that you can show using the Hilbert-Mumford criterion that the semi-stable locus for this is the set of points so x here is p1 to the n. So this is the set of points such that fewer than n over 2 points coincide anywhere. Okay, so semi-stability is to do with, points coinciding. It says that not too many points coincide. So what does the instability stratification, the HKKN stratification, what should that correspond to? Well, it's a measure of instability. So, you'd be on the right track if you guess that it has to do with how many points coincide. And that's exactly right. So the index set here is just going to be a sequence of integers. Goes like this, like n minus 4 down to 1 if n is odd and 2 if n is even. And y beta ss is the set where exactly beta points coincide at infinity in P1. So this depends on a particular choice of maximal torus. So the maximal torus I've chosen here is the one that goes T inverse on the diagonal. If instead I chose T inverse T, then I'd be working with a different positive Weyl chamber, which would the only difference would be a 0 instead of an infinity. Okay, and then what's the map to Z beta SS? This is exactly beta points coincide at infinity, and the rest are at 0. Okay, and then so what's S beta? So S beta, I told you, is the G sweep of Y beta SS. So this is the set where beta points coincide anywhere. And you don't have more than beta points coinciding anywhere else. So this is, a plausible measure of instability given what we know about the semi-stable locus. Okay. So the second example is, let me go back to coherent sheaves on Y. So we've heard probably about hard and narrow seam infiltrations. So there's a hard and narrow, if we have an unstable sheath, there's a hard and narrow seam filtration, which looks like this. So it's a filtration by subsheaves. This is F. And it has the property. So if I define F lower I to be F upper I over F upper I minus 1, so that this has the property that the reduced polynomials are decreasing, and all is semi-stable. Okay, so given that this is the case, you get another stratification of this locus I called Q into the Q taus, where Q tau is sheaves of type tau, and tau is just I just remember the vector of these polynomials. So tau is like P1, it's PF1 up to PF, I guess L. Okay, so this is going to live in like Q T to the L, I guess. Okay, so this is a stratification of this parameter space, and it also measures the failure of a sheaf to be semi-stable. It measures the failure of the sheaf to be semi-stable in the moduli theoretic sense, as opposed to in the GIT sense. So we now have in play for this Q 2 different stratifications. We've got the HKKN stratification coming purely from GIT, which measures the failure of GIT stability, and then we have the hard narrow seam infiltration, which measures the failure of sort of moduli stability. So it's reasonable to expect that there'd be some correspondence between these two things, and indeed there is. So let me tell you the theorem, which is due to Hoskins and Cohen. And this says that there exists a correspondence. Tau goes to beta of tau such that if you take the parameters in the construction sufficiently large, depending on tau, we have that Q tau is inside S beta tau as a union of connected components. And if you want to specialize this to the case of vector bundles on a smooth curve, then the two stratifications will actually sort of coincide. You don't have to worry too much about the union of connected components business. Okay, so finally, let me just talk about the case of curves in the last few minutes. Okay, so what about for curves? Right, so let's just go back to what I wrote about curves at the beginning here. Here we are. So what I said at the beginning here is that the GIT, the moduli space that you get is the moduli space of stable curves. That's the thing you get from GIT. And the stable curves, this is a condition on the singularities, more or less. So you need the automorphism group to be finite. You want the singularities to not be too bad. So you could ask, well, you know, what is the HKKN stratification for this construction, right? But there's even a question you have to ask before you can ask that question, because both the construction of coherent sheaves and the construction for curves depend on choosing some parameter sufficiently large, right? So it is actually not at all clear that the stratification should sort of asymptotically stabilize as you take these parameters sufficiently large. So one part of the theorem about coherent sheaves that I just talked about, one part of it is that, in particular, the stratification does kind of stabilize to something that is moduli theoretically meaningful. And this is not at all obvious in the case of curves. So the first question you have to ask is, does this stratification stabilize? And if so, does it stabilize to something which actually means something, right? And a first guess would be that it would have something to do with the singularities of the curves. So that's something that we don't know. We don't know the answer to this, but there is a partial result which I can give you now, just for a very, very special case. Okay, so here is a conjecture which says that the HKKN stratification stabilizes for, let's say, n sufficiently large in an appropriate sense. Right? Okay, and then one result that I can give you, which is something I did with Dave Swinarski, is that the HKKN stratification does stabilize in the following very special case. Okay, so I'm thinking now about rational curves, C, which are going to be embedded in P, let's say P R by OCD. So you take this thing, you take the point in the Chow variety that I talked about before, and you also need to ask for the curve to have a GM automorphism, and for the singular locus of this to be just one point unibranch singularity. So these curves are going to look like, let me try and draw a picture. They sort of look like this, and this is the point. This is the singular point here. You know, so it might look like I don't know, y squared equals the 2n plus 1, or you know, there's lots of different things it could look like. But the point is, you're only allowed to have one singularity, and that singularity has to be unibranch. So in particular, you can't have you can't have the curve sort of intersecting with itself. So this is for rational curves. This is not for g greater than or equal to 2. And the way that you can prove this is by the reason that this is so helpful is because it allows you to talk about the GIT of toric things. And there's a relationship for toric things between the weight polytope that you get for the Chow point and the set of subdivisions of the polytope of the toric variety, considered as a toric variety. So that's something that we're able to do, and I'm fairly sure that we can generalize this to get rid of the condition that that you have this automorphism, and that's because if you have a curve that sort of looks like this, has one unibranch singularity and is rational, but doesn't satisfy this, then there's a sort of canonical way to degenerate it to something that does have a GM automorphism. Essentially, you think about parameterizing the curve, just take the leading term in the leading terms in the parameterization, and that degenerates it to something which is homogeneous and has a GM automorphism. So we're actively working on generalizing this to other curves, and the hope eventually will be to first remove this condition and then to remove this condition. I guess to sum up today, what we've had is we've seen that reductive GIT instability has a kind of structure to it, and that if you want to, and that structure often has to do with moduli theoretic properties of the objects you're trying to classify. It's often geometrically moduli theoretically meaningful once you've set up a given moduli problem using GIT. And the final thing to say is that if you want to sort of complete the classification in the moduli problem to construct moduli spaces for the unstable objects too, then you need to use non-reductive GIT. And that's what I'm going to be talking about tomorrow and Friday. Okay, that's all. Thank you.
Thank you very much. Any questions?
Yeah, so Josh, for this asymptotic HKKN stratification on the Chow scheme, what do the strata correspond to geometrically? Is it by looking at fixed monomial semigroups for the unibranch singularity?
Yes. So yeah, what I didn't say is that you can associate to a curve, as in this theorem, given this singular point, you can look at what orders of vanishing of function do you have in the curve, and this gives you a subset of the natural numbers, which is called the semigroup of values, and that's a semigroup, and you can think of that as a discrete invariant which sort of measures the singularity. So just let me give you a quick example. If you take y squared equals x cubed, then you have something which vanishes to order 0, to order 2, to order 3, etc. But you don't have something that vanishes to order 1. So you're missing the 1 here. So the semigroup of values would be natural numbers minus 1, and the number of gaps you have in the semigroup, that's the genus of the singularity. So yeah, for these things, the only data that there is really is the semigroup of values, and that is what determines the HKKN stratification. And I believe that this is likely to be true, at least for unibranch rational curves in general, even without this GM automorphism. And the argument for that sort of heuristically would be to say that you take the curve, you degenerate it to the curve that has the GM automorphism, and you hope that you haven't changed what the worst one parameter subgroup is. So that's what you need to prove that for general unibranch rational curves with one singularity, the HKKN stratification is really indexing over these semigroups of values.
Thank you.
Any questions? So then, thanks Josh for the talk again, and then